Okay, so welcome back to the video lectures. First one of 2021. Woohoo! Don't be too excited. And honestly, we're just going to jump right into this because it is kind of tricky. So if you are a little bit lost in some of these examples, that's okay. It's really just going to take doing a lot of examples and a lot of problems together before you probably start to kind of get into the routine of these problems. But that's just what happened with related rates. And we're going to take it slow. We're going to do things together. And so hopefully you can get a grasp on optimization. So date before 1.8, topic 3.7, objectives, solve applied minimum and maximum problems. So do problem set 3.7 on WebAssign. It's a pretty short one because there's a lot of example problems in here that I really want you to try to think through with me during this video. So again, yeah, homework's not a little light today. And then lecture will be linked, obviously, when it's done. So one of the most common applications of calculus has to deal with finding minimum and maximum values. So think about how often you hear things like greatest profit or least cost or optimum size or anything like that. When we are dealing with such problems that involve maximizing a value or minimizing a value, we are performing what is called optimization. And this is like the related rates of chapter 3. So stay tuned. So we're going to kind of work through these problems in the same way. So just like we had the steps for related rates, we have the steps for optimization, but I'm going to kind of introduce those to you as we work through a problem. Okay, so example 1, perimeter problem. So this is there's a bunch of problems in here, but this is kind of one of the most basic, like this is optimization type problems. So find the dimensions of a rectangle with an area of 1,000 meters squared whose perimeter is as small as possible. So when you see something like as small as possible, as large as possible, that means that you're wanting to minimize or maximize a value. So you should think to yourself, oh, that's optimization. So our steps for optimization are 1, identify what is given and what we need to find. 2, write a primary equation for what needs to be minimized or maximized. 3, write the primary equation in terms of one variable. So steps 2 and 3 can be a little bit tricky because in order to write the primary equation in terms of one variable, that often requires the use of a secondary equation. Okay, so we're going to have to be looking at our picture, seeing what we're dealing with, and how we might write that primary equation in terms of one variable. Okay, 4, determine a feasible domain, and 5, determine the desired minimum and maximum. Since we're looking for a minimum and maximum values, we'll take the derivative, find our critical numbers, which again are when the derivative is equal to 0, doesn't exist, and then perform the first derivative test to show that we do in fact have a minimum or maximum. So remember the first derivative test, if it changed from increasing to decreasing, it's a max. Decreasing to increasing, it's a min. So again, we're going to need to use that sign chart once we find our critical numbers to determine if we do in fact have a min or a max. So without further ado, the perimeter problem. So first thing I'm going to do is I'm going to draw a picture, right? So I have a rectangle and I'm going to call this X and this Y, okay? And we want to know whose perimeter is small as possible. So step 2 says primary equation for what needs to be minimized or maximized. So what our primary equation is going to be is perimeter. And I know that the perimeter is going to be P equals 2x plus 2y because that's an equation for perimeter. So a lot of geometry formulas are going to be super useful in this unit. So I will remind you of those if it's a tricky one, but for the most part, like we can see perimeter right here, 2x, 2y, that's going to give me the perimeter. But again, step 3 is that I want to write my primary equation in terms of one variable. So in this case, I have an x and I have a y, but I want to write it in terms of only x or only y, okay? So I'm going to need a secondary equation. And in this case, I'm going to use area because I know that my area will be equal to x times y. And further, I know that my area is 1,000 meters squared, so I can rewrite this again as 1,000 equals x times y. And now it's really easy for me to write my primary equation in terms of one variable because I can use my area equation to solve for one variable. So I'm going to set y equal to, well, y is going to be equal to 1,000 divided by x, as I can determine from my secondary equation. And now my primary equation, I can rewrite as p equals 2x plus 2 times y, which is 1,000 over x. Okay, so now I have written my primary equation in terms of one variable using my secondary equation, and that is step 3. Step 4 is determine the feasible domain. This is kind of like a step that you can kind of do in your head because once you get your answers, sometimes it's like when we have an answer that's like negative time. We think, oh, that doesn't quite make sense. So in terms of thinking of a feasible domain, that's like, oh, would a negative length make sense? Not really. And then number 5 is determine our desired minimum and maximum. And since we're looking for a minimum and a maximum, we're going to take the derivative, find the critical numbers, and perform our first derivative test. So I'm going to rewrite my equation as p equals 2x plus 2,000 x to the negative 1, because I can use some fancy algebra to do that. Not really fancy algebra. So then I'm going to take my derivative in terms of x. So then I'm going to get, this is implicit differentiation because again, we are taking the derivative in terms of x. So on the left side, we have that p, so that's going to become p prime because p is not an x. But then over here, we have the derivative of 2x in terms of x, which is going to be 2 plus 2,000x to the negative 1, which is going to give us minus 2,000x to the negative 2 when I take that derivative in terms of x. So now I know that I have p prime is equal to 2 minus 2,000 over x squared. And then I'm going to rewrite that with a common denominator. So I'm going to have 2x squared minus 2,000 divided by x squared. Okay. And now I want to find my critical numbers. So what I'm going to do for that is, again, where my derivative doesn't exist or is equal to 0. Since our derivative is a fraction, we know that we can set the numerator equal to 0. So 2x squared minus 2,000 equals 0 to find out where our function is equal to 0. And our denominator equal to 0, x squared equals 0, to find out where our function doesn't exist. So x squared equals 0, square root, I'm going to get x is equal to 0. Over here, this is going to give me 2x squared equals 2,000, x squared equals 1,000, square root, and you would really want to think that 1,000 has an easy square root, but of course it doesn't. So you're going to get x is equal to the square root of 1,000. Okay, actually, I even forgot myself here, plus or minus the square root of 1,000. Okay, and this is where we kind of think about that feasible domain. So would negative square root of 1,000 make sense as an answer? No, so I'm going to throw that out. And I'm going to lastly do my little f prime sign chart, right? So I'm going to have x equals the square root of 1,000 right here. And then, oh, I also got x equals 0. Does that make sense? 0 as a length? No, not really. Because then I wouldn't really have a rectangle at all. I just have a line and it wouldn't have area. So anyway, I'm going to choose over here f prime of 1, a value to the left of square root of 1,000. And over here, I'm going to choose f prime of 1,000. Again, you can choose whatever values you want as long as they are to the left and right of your value, of your desired value. So over here, I get a negative number, and over here, I get a positive number. So I am changing from, in fact, decreasing to increasing, which indicates that I have a relative min. Check at x equals square root of 1,000. And then we have to go back and see the dimensions. We want to find the dimensions of the rectangle. So we know that x is equal to square root of 1,000. We know that y is equal to 1,000 divided by x, so equals 1,000 divided by the square root of 1,000, which is equal to square root of 1,000. So we actually have a square. So x equals y equals square root of 1,000. And our units here are meters. Final answer, square root of 1,000 by square root of 1,000 meters. And we know that that's a minimum because we proved it. All right, so moving right along, box problem. So finding a box with an open top is to be constructed from a piece of cardboard with dimensions 16 by 30 by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume the box could have. So again, we are going to start with a picture. A box is being constructed by a piece of cardboard with dimensions 16. My 1 came out kind of weird there. Let me give myself a little more space. We're going to have dimensions 16 by 30 by cutting out a square from each of the 4 corners. So we're going to cut out a square from each of the 4 corners and bend up the sides. So hopefully you kind of see that if you cut out these squares, you would be able to bend up the sides of this sheet of cardboard and get a box. So find the largest volume that the box could have. So largest volume indicates that our primary equation is going to be volume. So primary V equals length times width times height. Okay, so we have 3 variables and we want to write this in terms of 1. So for our secondary equation, we're really going to have to take a look at our picture and see what's going on here, okay? So I'm going to call this X because I know that it's going to be a square and that each side is going to be the same, so that all of these little lengths that I'm cutting are going to be the same. So I'm just going to call them X. And then that gives me some information that I can use for my secondary equation, right? So for example, length I know is going to be equal to 30 minus 2x, because the length of my cardboard box initially is 30, and then I'm taking out 2x. Okay, so that's length. Height is going to be equal to x, because that's what I'm folding up. This little side that I cut out, I'm going to fold up. So my height is going to be x. And following this, my width is going to equal 16 minus 2x. Same thing as length, right? We're cutting out 2 little x's on each side and then folding it up. So therefore, now I can write my primary equation in terms of 1 variable, because I know that v is going to equal length, 30 minus 2x, times width, 16 minus 2x, times height, x. Okay, and now you guys can have some fun foiling that out and then multiplying the x in, but you should get that volume is equal to 480 x minus 92 x squared plus 4x cubed. Okay, and now I want to take my derivative of that in terms of x. So again, on the left side, implicit differentiation, I'm going to get v prime is equal to, and that's going to be 12x squared minus 184x plus 480. I'm going to want to set that equal to 0 because, again, I want to know where my derivative is equal to 0 or doesn't exist. This guy is going to exist along the whole real number line, so I'm going to set it equal to 0. 12x squared minus 184x plus 480 equals 0. I'm going to factor out a 4 to make this easier on me to factor. So 3x squared minus 46x plus 120 equals 0. So that's going to give me 4 times x minus 12 times 3x minus 10 equals 0. I can set them individually equal to 0, 4 equals 0, not an answer. X minus 12, I'll write this up here. X minus 12 equals 0, x equals 12, 3x minus 10 equals 0, 3x equals 10, x equals 10 thirds. So I'm going to stop here, and again, I'm going to think about my answers. X equals 12. Look at the dimensions, or look at my picture. If x is equal to 12, I have a funky looking box. Okay, so x equals 12, not a logical answer. So that leaves me with x is equal to 10 thirds. So I'm going to draw my little sign chart. 10/3 right here. And then I'm going to have f prime of 1, and I'm going to choose f prime of 10. I like choosing like 1s and 10s and 5s because they're easier numbers. So I'm going to plug that in, and I'm going to get that I get positive over here and negative over here. So I'm going from increasing to decreasing, which indeed is a max. So I have a relative max at x equals 10/3, check. And then I'm just going to use x equals 10/3 and plug them into my secondary equations to find length times width times height. Then once I have length, width, and height, I can do v is equal to length times width times height. So again, I want you to do this part. Plug in x to length, width, and height, figure out what length, width, and height are. Then volume is going to equal length times width times height, which should equal approximately, let me erase that and make a squiggly equal sign, which should equal approximately 725.93 inches cubed. That is my maximized volume there. Okay. So I'm going to clear this, and then I think I'm going to have you try the parabola problem, okay? So I want you guys to try this one on your own. It's a little bit tricky, but again, draw your picture. Actually, I'll help you draw the picture. Okay, find the dimensions of a rectangle, largest area, that has its base on the x-axis and the other two vertices above the x-axis, and lying on the parabola y equals 8 minus x squared. So my parabola is going to look like this, 8 minus x squared. And I have the rectangle of largest area that has its base on the x-axis, so right here, and its other two vertices above the x-axis. Oh, I drew a weird rectangle. So it's going to be like that. And lying on the parabola. So these 2 points are going to be on the parabola. This is going to be y, and this right here is going to be x, okay? And then I want to have a primary equation, which is going to be area, which is going to equal what? And then I'm going to have a secondary equation, and that is going to be in terms of one variable. So use what you know about this parabola, what the heights are going to be, what your rectangle is going to look like, and try to figure out if you can find a secondary equation that's going to be, I'll give you a hint, it's going to be y equals something. So see if you can use what you know about that parabola to figure out what y is going to equal in order to write area in terms of one variable, find your relative max, because we are largest area, and then go ahead and maximize this problem. And so that is all for now. I think we're gonna do the rest of these problems in class time. And one other one that would be easy to do is I want you to also try the soup problem, okay? So try the parabola problem and the soup problem for homework. And then there's like 1 or 2 more on WebAssign. And that is all I have for you guys today. We will, again, be doing lots of optimization problems. So if you're confused or you're like, I don't understand what's going on, I want you to not give up, try the problems, and then we will go over them in class, and I'm available in tutorial, blah, 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 etc. Have a lovely day.